And then we have the discussion session afterwards, which you can ask as many questions as you want. Maybe MBL will come up.
You mentioned mono F noise. And of course, I mean, mono F noise is extremely ubiquitous. I mean, are you saying that, I mean, all these systems are sort of at near a transition from sort of, in a way, integrability breaking? That's something I can't believe.
It seems likely. But again, you have to be careful. By sort of integrability breaking can be like breaking some symmetries, some conservation laws. So I'm not making a claim that any integrability breaking perturbation leads to 1 over F noise. I mentioned there are examples where it's like you have special, say, commuting classical limits or special perturbations where you see this super slow dynamics. But there are also examples where you immediately with perturbation break all the symmetries. And then you have like normal, almost exponential decay. Like exponent depends, of course, on integrability breaking perturbation. The smaller the perturbation, the longer you decay, but you have this exponential thing. And to us, it's like really open problem, like when you have this. But my guess that if you see 1 over omega, it basically means that you have like nearly integrable. For 2-level systems, it will work perfectly. If I have, I don't know, some gas of 2-level systems, I have this conservation laws, and then if I weakly couple them, actually this 1 over omega will be expected, almost irrespective of the spectrum of bare 2 levels. It's like basically the point is that with perturbation, I cannot couple all of them at the same time. So yeah, it's a very interesting question. We keep it in mind, but this seems to be related.
Okay, so anybody else would like to ask a question? For now? You? Yvonne?
So can you explain what you mean by CAM in the quantum case? So in the classical case, there's a well-defined definition, but so in the quantum case, can you re-explain? I missed.
No, but it's more like my analogy. So of course you cannot, well, there is one possible explanation which actually people in MBL came up with, which is probably true, but one needs to check. It's what people call fragmented Hilbert space. So in the sense that if you look into, so what is KM? It's basically mixed phase space where your kind of trajectories don't go everywhere, but you have sort of chaotic regions and so on. And they define fractal dimensions in Hilbert space. When you look into eigenstates, you see that participation ratio among, say, Fock bases is not, doesn't scale with Hilbert space size, with some power of Hilbert space size. So, but I kind of like to connect both things in a way non-observable, because even classically, once you go to many degrees of freedom, it's very hard to define what's fractal dimension of phase space, because your trajectories are super complicated. So, but in both cases, like quantum classical, you're comparing all the models. If you break weakly integrability, you have very similar behavior at low frequencies. And the moment you get asymptotic behavior, which does not saturate, so it keeps going. It keeps going. Again, quantum mechanically, there is always Heisenberg scale. So basically what I'm saying, if you have asymptotic low frequency behavior, which lasts all the way up to Heisenberg scale quantum mechanically or to 0 classically, and this doesn't saturate, this indicates that you have this chaos. In a way I define it's very physical. And in all KM regimes, at least we checked, you have this behavior. So the reason I'm calling it KM, not because I know relation, mathematical relation to this theorem, but because all KM systems we know, they behave exact
okay, so KM is defined by the 1 over omega divergence?
It's not always 1 over omega. What I'm saying, 1 over omega emerges very frequently, but you can have other powers. So for example, if you take this classical models with strong integrability breaking perturbation, but still non-ergodic, you can observe like power of 0.6. When people take, I know, Anderson insulator, it's another example, you get some other power, I forgot, it's like in between. It's always less than 1 and bigger than 1/2. It's also around 2/3 and so on in 3 dimensions. The power depends. So actually, if you go to infinite dimensions, approaches 1/omega. It's interesting. But the power at finite dimensions less than 1/omega. So you can have what people call subdiffusive behavior and so on. But 1/omega is like limiting behavior, and in some situations it does appear. So, but in which I don't know.
Okay. Thank you.
Okay, so then, in the interest of time, then we can go for a break and then come back for more questions. For all speakers. Thank you.